presentation, we'll show how we can leverage Capella and the ARCADIA methodology in the specific context of satellite systems. So a quick brief about the table of contents. We'll first introduce ourselves, and we'll talk about the specific domain that we're working on, which is satellites and satellite constellations. We will talk about the problems that we are trying to address through MBSE and specifically Capella. We'll talk about the solution to those problems using Capella. And finally, we will conclude, this was a pilot project of sorts, and we have some conclusions from that. So for a quick introduction about myself, I'm George Savio. I'm one of the systems engineers here at Pixxel. Now, Pixxel is a startup. We are about 200 people, and we are attempting to build a health monitor for the planet. And we want to do this by creating a constellation of Earth observation satellites that capture hyperspectral data. So we'll be capturing information in the electromagnetic spectrum, but we capture hyperspectral data, and that differs from normal imagery. A normal image will have 3 bands, red, green, blue, but a hyperspectral image will have hundreds of bands, and that allows for more insights to be extracted because you're able to resolve the spectrum with more resolution, essentially. And so we build and operate these hyperspectral cameras. So far, we have launched 3 technical demonstrations. We have captured imagery from them, we have processed them, and we have used them in a bunch of projects. Customers who use these imagery, span across multiple industries such as forestry, mining, agriculture. We also are involved with certain governmental agencies. We had recently won a contract with NASA, and we work with other governmental agencies, including those in India. We are currently in the process of getting our Firefly satellites ready, which is the satellite that you saw in the first slide. This is going to be part of our commercial grade of satellites, and we're going to launch in January 2025 on the SpaceX Transporter mission. 3 of the satellites from the constellation will go up, and a few months after that, we will have another 3 go up, and after that, even more. We hope to have at least about 24 satellites in the entire Firefly constellation.
Yeah. Good morning, all. I'm Rahul Joseph. I'm a model-based systems engineer. I work at BlueKei Solutions. I did my master's in automotive systems. I'll take this opportunity to introduce my colleague, partner, Tanmay Dube, who works as systems engineer here. But due to his personal commitments, he couldn't be with us. So moving on, BlueKei Solutions help enterprises and startups implement system engineering transformations through digital engineering. Currently, we operate in India and Asia Pacific. Our clientele includes organizations in aerospace, automotive, medical field. And for our clients, we provide frameworks for systematic approach so that solution development can happen. And also it is important for us to give a very tool agnostic approach to the solutions because tool is just an instrument that enables us to develop the solution. Also, it is important at BlueKei that we focus the approach on systems engineering practices to make sure that the clients have an impact on their business outcomes. So this is a project, the collaboration between BlueKei and Pixxel to solve some of the problems identified at Pixxel, which we're going to talk in this coming slides. Over to you, George.
Yeah, so before we dive into the main parts, we'll give some background on satellite constellations. I think there has been enough context given even by our previous presenters, but we'll give a short one nonetheless. So while the satellites are usually the star of the show, there are other ancillary or supporting systems that are required in order to finally deliver value to the end customer. And so I will just go through the parts that make up a satellite constellation. First, we have the satellite itself, and the satellite basically, at least an imaging satellite, only has 2 main functions, which is one to sense which is to collect the data and then to be able to transmit that data back to the ground. And the ground is therefore our next entity, a ground station, which is able to communicate with the satellite. It receives the imagery that the satellite has captured, and it is also from where we operate the satellites. The satellites are not the most smartest. They require some level of humans to operate them, and so the operations are also done through the ground segment, of which the ground station is a part of it. And finally, the imagery by itself might not be very useful. It has to be processed so that insights that are useful for the end customer can be extracted. And so there are data processing pipelines that exist that ingest the satellite data and produce actionable insights. While we've just explained the different parts of a constellation, while discussing model-based systems engineering, we'll also have to discuss the teams that are involved in designing this, because that is what we're trying to solve. We're trying to solve communication between these teams. So to quickly give you an idea, within the space division over here, we have about 15 to 20 different teams, depending on how you define or how you count teams, which is a lot of teams. And these teams include mission design engineers and mission operation engineers, who look at very high level objectives, like what must the constellation achieve, and then they'll either design and operate accordingly. We have systems engineers such as myself. We have architects who come up, who help architect the satellite, and all the system functions that the functions of a system engineer are done by this team, requirements, interfaces, configuration management, etc. We have mechanical engineering teams. So this is usually structural engineers, thermal engineers, propulsion engineers, mechanism engineers, etc. On the electrical side of things, we have power system engineers, digital engineers, like RF engineers. There are a lot of control elements on the satellite as well. And so we have attitude control engineers. Attitude is just the fancy term for orientation in the industry. And GNC, which stands for guidance, navigation, and control engineers. Obviously, there are a lot of modules within a satellite that require software or firmware. And so we have a bunch of these engineers as well that will design and code up this software. And finally, to test everything that all the other previous engineers have made, we have specific test engineers to test out all of the above. Now, we will talk about the problem that MBSE is trying to solve. So over to Rahul.
Yeah. So as George mentioned earlier, satellite is a very complex system and there are many teams involved in it. So usually what happens is when we have many teams involved, the design decisions and the conclusions are scattered all over the place. So which leads to have a fragmented information storage, making it a challenge to ensure any consistency throughout the development stage. Also, this problem seeps into one more problem, which is the lack of having a holistic view. Now that we have everything at different places, to have this bigger picture view, it gets very difficult, and then leading to potential gaps in design, development, and integration. So these are the problems coming from the systems point of view, and then we have the teams that are working. And usually what happens is we have different teams which is focused on specifically their disciplines. Often they work in isolation, so eventually leading to siloed multidisciplinary teams, making it hard to coordinate effectively, and also achieving alignment to a project goal gets more difficult to that. Lastly, most of the decisions are taken at a very high business level and they flow throughout, and then they reach the downstream engineering to implement them. So if there is a trace that misses between these decisions and the implementation, it's hard to gauge the impact of each stage of development, and also to ensuring alignment with the strategic goals of the company. So now moving on, so that we have understood the problems we are facing, for the approach on how we are solving it, all of the problems addressed before, implementing SE practices solves them in a very systematic way. But MBSE adds a certain level of additional benefits to it. So that's why we choose MBSE for this approach. And having MBSE, provides a centralized place where a model driven environment where everything can be stored at one place. Now, when we have everything at one place, adopt the bigger picture view helps us to recognize the dependencies, interactions, and any conflicts in the entire system. Also, now that everything is getting complex and the systems are growing further, adopting MBSE while designing becomes the first step to get into this digital thread. Now that we have established that we're going with MBSE to solve this approach, there are many tools available at this point. So now we are specifically choosing Capella and Arcadia methodology for the approach, mainly because of one peculiar reason is that it's an open source platform, meaning that there is no hassle for licenses, and all of the 200 people team can jump onto the model anytime, model what they are doing, and consume it at the same time, making it easy to scale. Also, the community support available for Arcadia and Capella helps us to identify the problems and get support from the teams. Finally, the methodology and tool allows for representation of systems quickly, so that even non-SE engineers can consume it and then work on it. Moving on, coming to the specific implementations of how Capella will solve this. So the complex system can be sliced down and modeled individually into functions, requirements, blocks, interfaces. So all this way we can systematically break the complex systems, and then Capella offers a systematic after the breakdown we can generate multiple views and viewpoints so that the different teams involved will have a better understanding of the entire system. So let's see how it gets implemented. Over to you, George.
Yeah. Now, the system model is not going to be static. It is going to change as a program or as a mission evolves. The purposes that it has to serve or what needs to be modeled changes over the phases of the satellite. So again, just for a little bit of context, we thought we just explain the different phases that are typically associated with a space mission or a satellite development project. So what you see here is just an example phases. I've borrowed this from the European Council for Space Standardization, which is what ESA uses as well. But all space agencies or all space organizations will use something similar, or whatever they use will be equivalent to this. And we can just take our handy systems engineering V to explain how these different phases map uh, to the different parts of the systems engineering V. It's pretty straightforward. So phase A corresponds to the top left half of the V. Phase A is where we talk about the concept of operations, where it's decided the elements that make up the constellation, the space segment and the ground segment. What is it that they must achieve, keeping them as black boxes, and specifying what they must do and how they're going to interact with each other. And this is essentially the concept of operations. In phase B, we start looking into the system itself and deriving those specific requirements and start to think about how these might be implemented. And so you have a preliminary concept or a preliminary design that gets developed in phase B that meets the system requirements, which meets the high level mission and customer requirements. In phase C, we go into detailed design where you fully flesh out how a component is going to be made, what are its parts, and how it is going to be made, so that with all of this specified, you can actually then implement it, you can actually build it, be it software, be it hardware, anything. Uh, with that, we then move on to the right side of the V, and in phase D, we basically, as all of you might be aware, we start assembling the satellite, testing it in stages, and this is done recursively from unit to assembly to subsystem all the way to satellite. And finally, in phase E, the satellite is actually deployed. It is launched by a launch vehicle, and then it is operated. So while this is how most people in the industry would view it, most systems engineers in the industry would view this. How do these map to the different stages of modeling in Capella? So, as you all might be aware, there are 4 stages. There's the operational, system, logical, and physical. The operational analysis more corresponds to the concept of operations, where you would be taking maybe customer requirement, mission objectives, and modeling that. In the system requirements, we'll be looking specifically at what the satellite has to do as a black box. And in the logical architecture, we start specifying the parts of the satellite itself. And in the physical architecture, it is explained the full breadth of all the interactions and all the functions that every individual part of the satellite has to do is covered. And so with that context, we can move on to the first phase, which is phase A, which is the mission analysis. So here, what happens is that there's a mission design team, and they will ingest customer requirements or any other mission objectives, and then they try to translate that into a sort of constellation design, where again, they specify what must the space segment and what must the ground segment be capable of, so that if they perform their functions and they interact in the way that is prescribed, we can get, or we can realize the needs of the customer or the mission. And so they usually end up performing orbital simulations in order to answer such questions, such as what orbit must we be in, how do we achieve the latency required by the customer, how quickly must we be able to image any given location. All of these are iterated upon, and what we end up getting essentially is a reference mission profile. And so what the reference mission profile does is it essentially spells out what the satellite and what the ground segment, obviously treating these as black boxes, must be capable of doing. And the reference mission profile can be visualized. If I'm not wrong, I have a video that I can show. Yeah, so this is an example. I'm assuming the audience can see the video, but this is an example of just a small snippet of the reference mission profile, where here, what in red is the orbit, and the dot on the orbit is the satellite. The satellite is making a pass over one of the areas of interest, which is in the African continent in this example. And so the video has gone over quite quickly, but the satellite has been tasked with taking an image over the subcontinent, African subcontinent, and then you can see in India there is a ground station in Hyderabad where that image is then downlinked. So this is just but a small example of what the reference mission profile will contain. The reference mission profile in this manner will contain information on what or prescribes what the satellite and what the ground segment must be doing, not just in this specific scenario, but in scenarios throughout, such as in launch or while commissioning or while maintaining the orbit of the satellite, for example, or if it has to avoid collision with another satellite, or if it has to deorbit itself. There are multiple such cases or scenarios that comprise the final reference mission profile. This is just a representative example. So this reference mission profile is now the input for more detailed design of the satellite. And if we want to create traceability all the way from the start, there needs to be some way to input this reference mission profile into Capella. And so in the reference mission profile, as a satellite systems engineer, obviously the system of interest is the satellite. And what the reference mission profile, as you have seen, is it's describing what the satellite must do. And so here we can start actually at the system analysis level, and we can input the reference mission profile into the system level. And so how do we do that? We will have to break the reference mission profile into multiple snippets. And these different snippets correspond to different capabilities of the satellite. And so we can use the capability construct to formalize them into the model and associate them with the system, which is what you are seeing on the right side. And then you capture the dynamic, the dynamic performance that is expected from the satellite as seen in the reference mission profile using sequence diagrams. And so in the sequence diagrams, you're not only capturing the functions that need to happen, but you're capturing them in the sequence and in the durations that you expect. So the example that you see here is an interaction between the system and the ground station, similar to what was seen in the video, where the satellite is pointing to the ground station and initiating downlink. So the same is being represented in a exchange scenario, basically. And so what you will be doing with the system model throughout phase A, as and when the reference mission profile is maturing, you can start modeling and inputting basically the reference mission profile into the system analysis level. That is what we envision that needs to happen in phase A with respect to the system model. For phase B, which is the formulation stage, we need to move into more detailed design. And so we have essentially answered a few questions. We must be able to define what the system must do, and we need to be able to create the basic design of the system as well. And so to define what the system must do, you must know what its functions are. So you need to be able to break down the requirements at the satellite level into what the parts should do. You need to be able to tell how these different parts are interfaced and how they're going to be working together, and specify if there are any performance specifications as well. Those also need to be specified. And in the basic design, you're essentially just specifying the design. You have to outline the overall layout of the satellite and essentially spell out how these things are going to be connected to each other. So these are the broad questions that we are trying to answer in phase B, and the model must help us with that. And so we need to answer these questions through the model in phase B.
Like George mentioned, the first important thing is to define what the system must do. To do that, what we start off is to write the requirements, but this is the first step of the V model. So what we have decided to do is to have an Excel template where we define how the system is doing, what it is doing, how precise it is doing, is there any time gap, is there any dependencies on others. So each of them will become independent columns. So in this way, we can understand if there are any gaps in our requirements. So to do so, we followed in course writing guidelines to write correct and complete requirements. And once the requirements are elicited, we gave it to the technical teams to write structured requirements, and this has helped us to formalize what the system must do. And moving on, once we have the requirements with us, we 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 did we moved them to the modeling aspect. We moved them to the model, and also not only that, the requirements now exist in the model, they can be linked and traced with their respective model artifacts. So requirements can be mapped with other requirements, creating a child parent relation. Requirements are mapped to the system that is performing it, and there are functions that the systems are performing, and there are exchange elements, and there are interfaces as well. So all of these individual the attributes of a requirement are added to their corresponding artifacts. So not only that, Capella also offers trace manager, which can be used to have a centralized place to change, modify these traces between requirements and other elements. So let's say, for example, of if we want to expand the scope of the model and we bring in new capabilities or new systems into the model, so we can quickly jump onto the trace manager part and then do the traces on how these new elements are added and how they are linked with the requirement set.
So coming back, so in phase B, which is the formulation stage, there needs to be increasingly more clarity for downstream engineering. So the basic question that we want to answer here, or what we have to start answering, is the system functions that we derived at the system analysis level from the reference mission profile. How do these get implemented? And so we need to answer these questions, like what components need to be involved in order to realize this? What functions must they perform? To what specification must these functions be performed? And how are these components interfaced? And we'll highlight this with an example or two. We'll first take the example. One of the system functions and the logical functions would be that the satellite must be able to determine its orbit. And this is usually a capability within the guidance, navigation, and control of a satellite. Now, it is very simply put as determine the orbit at the system level, but for the engineers that need to implement this, and there are a lot of them, they need to all be clear that the solution for this is as expected, as each person might have their own idea of what is happening. So to realize this, for example, you will have algorithm engineers or hardware engineers or embedded engineers, all sorts of engineers. And so we need to have in this stage a consistent set of views to make sure that everybody is actually on the same page. There's always so much nuance, and words can be misleading sometimes, but these specific views provide more clarity, make things less ambiguous. And so this is an example where we have taken a system level function, say determine the orbit, and we have broken it down. We understand what are the components that need to be involved in this case. We understand what are the functions that each of them need to be doing. If there are any performances specified, we can also put those across in using the requirement model element. And we can also specify how these things are interfaced with each other. Obviously, one view is probably not going to be enough. We might need other information to specify also the time series information. And so that's what you're seeing. All of these functions on the right-hand side need to happen in this time sequence. So all those timing related information is also kept in one place. And on the left, we are just showing how all of these trace back to the, in this case, you're seeing the physical level function, but this obviously is tied to the logical and system level functions. Another example where there needs to be more clarity is on monitoring and commanding. This is a critical aspect of satellite development, because once a satellite is launched, you have no way to physically access the satellite. And so if anything goes wrong, you need to ensure that you can still monitor and command it, and that you can monitor and command individual parts of the satellite as well. So I am essentially trying to say that monitoring and commanding is often overlooked, and we have found that we have discovered that it requires a lot of teams to interact. So before moving forward, I will give you a little more context on monitoring and commanding. This is achieved by using by using telemetries and telecommands. So what are telemetries? Telemetry is any piece of information about the state of the satellite, and not just necessarily the state, but it is information that will help us understand what is going on in the satellite. Uh, it is needed to obviously monitor the satellite to make sure that everything is working nominally, and if it is not working nominally, to understand what is gone wrong. So some examples include power levels. This could be the battery charge, for example, temperatures of different parts of the satellite, the satellite's attitude, the statuses of different components, etc. So telemetries are information that is received on ground from the satellite, and telecommands are instructions that we send to the satellite. So the operators will send telecommands, and the purpose is to tell the satellite what it needs to do. And so the satellite is not an intelligent piece of metal. It needs to be told what to do precisely. And so for operating and to meet the objectives, you need to send different sorts of instructions. And so the instructions could be capture image, you can update some software, or adjust an orbit. Just examples of telemetries and telecommands. Now, why we wanted to also model this, the monitoring and commanding subsystem or the capability of the satellite, is because this is one area where there are many interacting groups. And once again, with many interacting groups, there is scope for ambiguity, confusion, or just inconsistency between what different groups think. And so if I can maybe show a visual using these Capella diagrams, each box is representing a different set of interaction. So in the first box, we have all the engineers that are related, that are involved in the development of a particular component. They will obviously be discussing and designing amongst themselves, and will have one particular understanding of how things need to be monitored and commanded. And then in the box to the right of it, we have these component engineers then interacting with system level engineers, be it the system architect or even like an operational engineer, where those engineers are interested in not just the component, but the component's interaction with everything else. And so you will need another set of documents to be exchanged over here to make sure people are on the same page, or it's another set of interactions. And then these system level engineers are then interacting with the software engineers who are designing system software in order to command and monitor at the system level. And so this is also another interaction, another place for confusion. And finally, the flight software engineers have to interact with the ground segment engineers who are developing the systems on ground to manage and process the satellite information, the satellite telemetry, as well as the operators. So there are many engineering teams involved. And so this is a good place where we can use the system model to formalize things and act as a single source of truth. So how we did this is by using the data modeling capabilities on Capella, and the telemetries and telecommands are modeled as exchange elements. So what you see on the left-hand side is an example of a telemetry, the orbital state, and using Capella's data modeling feature, we have shown how we can precisely define this. And on the right-hand side is an example of an imaging telecommand. So for those not familiar, the kind of red color box represents an exchange element, which is a sort of model element in Capella. And in the yellow, pardon, I do not know colors very well. So the yellowish looking box talks about the different attributes that are involved with the telecommand that are useful or that are needed in order to execute the telecommand. So this is how we formally define them within the model. We also used another model element, which is the interface. And we defined two interfaces. And this is using the CEI diagram, which is the contextual external interface diagram. And we have two interfaces, a telemetry interface and a telecommand interface between the two interacting entities, the satellite and the ground segment. And in this diagram as well, we can add, if needed, other attributes or values, such as the one shown in the example. And then when we do this, what we can do is we can allocate the telemetries and telecommands to this particular interface. And that's what we have done. That's what you're seeing on screen right now, where the orbital state telemetry is just been allocated to the TM interface, and the telecommand model element has been allocated to the TC interface. And why this is useful is it allows us to get a complete list of all the telecommands and telemetries, and it makes sure that we have one place for all of this. And so in the future, we can extend the model, directly read from the model using a bunch of other tools. And we could also populate sheets or any other artifacts that are more relevant for the design or implementation for the engineers. And so once again, this is a place, this is how we can put all of this into a single source, allowing us to defining the telecommands in this way also allows us to include this information in the other models. As you might have seen earlier, a telecommand contains arguments or attributes that need to be used in its execution. And so by associating it with different functional exchanges, we can understand how it is being consumed. And since it is defined properly, anybody who is trying to implement something in any other feature, for example, in this example where the satellite is slewing, they can understand how that information is going to be defined. Now, that mostly wraps up phase B, wherein what we have done is all those different snippets from the reference mission profile that have been put into the system analysis level, we have started breaking it down and started specifying what the components need to be doing. And so essentially, we have given a blueprint of sorts for the different components. We have specified what it is that we expect from the components, so that when these components come together, the system will emerge as expected. And so in phase C, which is the design and build stage, the system model should now contain enough information that allows for the implementation of these components. And so in this stage, we envision that the system model will be used as a blueprint or a reference or a guide uh, in order to clear any confusions that might happen while either detailed design or while implementing the specific components.
As George has explained, the left side of the V and the implementation, which is the bottom of the V, let's look at how the model integrates on the right side of the V. So since we already defined the behavior of the system once, we use sequence diagram for that. So we can use this, and the test engineers can create test cases based on these inputs. So the same artifacts can be used to plan test cases and test case attributes. So how it's going to look, so if for a test engineer, let's take this example for this sequence diagram. So when the handshake happens between the system and the ground segment, so that becomes the entry criteria that defines the scope. And then you know that what are the functions that you need to test during this sequence. You can also test the performance that needs to be achieved during this, and then it kind of gives an idea on the entry exit criteria as well. So in this way we can reuse the artifacts that were developed on the left side of the V into the right side of the V. Moving on. So a brief, a quick conclusion on what we just presented right now. The Capella model acted as a single source of truth to build, change, and maintain satellite development. Also, modeling the system into OA, SA, LA, and PA. In this way, we have broken down the complexity of the model, the system, and the model semantics help to define some standardizations and the relations between the satellite data, which in way forced us to have a degree of consistency between the systems and the interactions. Uh, this is continuing. That's from the system's perspective. Now, if we look at it from the team's perspective, the multiple teams that are involved on the development phase have multiple views created and managed, and they are available at the single place in the model for them to consume. Also, as George explained, that we defined the exchange elements and the interfaces between the systems. This helped in adding additional information and which complements the ICDs to have a handshake between the technical teams. So this is how we concluded the solved the complexity of the teams involved. And during this development phase, these are the benefits we realized throughout. So one is straightforward: the complex system has been modeled systematically and then broken down to break that complexity. And also having them in the model, Capella had allowed us to have supplementary visual diagrams which non-SE teams can consume easily, and they have a better understanding visually. Since we already have the requirements in the model, which helped us to write a precise requirement, concise requirements, and which allowed us to handle the requirements. So allowing us to do MBRE model based requirement engineering. And the establishment of this process ensured that any impact or any change or any decision that was made will be understood by the entire team involved. And one quick example that I explained previously, how we've used a sequence to derive test cases. So similarly, the artifacts can be reused to reduce the lead time in the product development.
Yeah, so we had a month or two to implement a pilot project, and there's obviously a lot more scope in integrating a system model into other parts of the satellite development process. And so one is including it a bit earlier, and to also include information about, I mean, trade studies are an inevitable part of any design process where you're going to trade off many options. One thing that can be added into the models at some point in the future is information about these trade studies, the options that were considered and all of that can also be included into the model. Another aspect is also including all of this into phase E of a satellite project, which is operations. And so usually the satellite development team will pass on a set of documents, such as a user manual, to operations teams. But if the model itself is structured in a way that is more friendly or navigable by operators, we can instead just share these system models with the operations team directly for them to be able to understand the inner workings of the satellite. And yeah, finally, it is about creating a pipeline wherein a model from one project can help initiate and jumpstart the development of another project. Because as was noted even by the previous presenters, what a satellite is going to have to do is not going to change very radically across missions. And so at the initial stages, when so many things are being traded off, you cannot keep a lot of things in mind. But by reusing these models, we can quickly understand and ensure that early on we are thinking about as many aspects of the satellite as we can. So that's where that's a big advantage of reusability, wherein it saves time. It saves time. You don't have, for one, you don't have to keep doing all of this. But since we already have very detailed models, we can ensure that we're not forgetting things when we start another mission as well, and we're accounting for more things. And so I think that essentially concludes our presentation. And if there are any questions, we are open to hear.
Okay, thank you for this presentation. So, first question we have: how do you treat non-functional requirements? For instance, sensing performance is typically linked to aperture which drive mass.
So one way to at least express them in the model, there's either you have to directly put the requirement directly, or I believe Capella also has the constraint model element, which can also serve this purpose to some extent. We haven't in this project really thought about these aspects. They are an equally valid aspect to it. So as I view it, there's form and function for any system. And while we have specified a lot about the function as well, mostly about the function, the form is important and it drives things like mass, for example. We haven't addressed that yet, but I believe there's a property value manager as well, which allows us to do it. But right now we do that separately outside of the model. The model right now helps people understand the performance, like the function that needs to happen.
Okay, thanks for this answer. Next question. How do you make sure that any upgrade or modification of a requirement in your Excel sheet gets reflected in Capella?
Okay.
So to answer that, it's done manually right now. So we make changes in the Excel, we come back, we iterate it, and we add. So we use a requirements viewpoint plugin to add it to the model. So automatic updation is not in scope for us, but I believe that Capella can offer an extension where you can connect it with Polarian and to have a couple of requirements written there, and thus any updates or changes, they can be brought into the model, but that was out of scope for this project.
Yeah, I mean, it will have to be done manually. There aren't, and that's just something that you'll have to live with.
Okay, did you also consider the retirement phase? Yeah.
So, for example, in the retirement phase, at least for satellites, you have to be able to decommission and deorbit the satellite. And so, for the satellite to be able to do that, it's a capability in itself for the satellite. And so, that is something that you can model. That is something that you can show through the model how the satellite is going to implement this. If that is what you meant, that can also obviously, since that is just another system capability, that can also be shown in the model. Although in this particular model, you don't see it.
Okay. Did you use system to subsystem transition to manage the complexity of your system?
We haven't, but this is something that we have thought of as well, that some of the components, suppose an avionics module, it might end up having to do a lot of functions, and it becomes a complex system in its own right. And so that is a candidate for one of the things where we thought we could spin off its own model. But we're still at a very early stage of adopting this even. So we haven't, but we have thought about where all we can include this.
How do you formalize the exit and and entry criteria of your exchange scenarios?
Okay. I think, Rahul, this is
Yeah.
about what you were.
Yeah, so what we did here was to have a sequence first, and then it becomes as an input to the test engineer. So we didn't dig deep into writing preconditions and post conditions in the model at the moment, but the idea was that it makes it easier for teams to consume. So maybe in the future scope, when we want to expand it, maybe that's where this could be helpful for the test engineers.